Ton 618 carries a published black hole mass estimate of 66 billion suns, yet no telescope has photographed the object being weighed. How can astronomers estimate a black hole this massive from quasar light, and how certain is that number? Ton 618 is established as a quasar, an extremely luminous active galactic nucleus powered by gas falling toward a supermassive black hole. That sentence matters because it separates the engine from the light. The black hole itself is dark. Its event horizon sends no light back. Around it, gas is compressed, heated, ionized, and driven into motion. That surrounding environment is what telescopes detect. At Ton 618's distance, even powerful telescopes do not show a close-up structure. They record a point-like source, colors, brightness, and spectra. The image is not a portrait of the black hole. It is evidence from the region around it. The famous mass is therefore not a direct weighing. There is no orbiting star tracked around Ton 618 the way stars have been tracked around the Milky Way's central black hole. There is no horizon-scale radio image like the images made for M87 star and Sagittarius A star. For Ton 618, the case begins with light spread into its component wavelengths. A quasar spectrum looks like a barcode written by atoms. Gas near the central engine emits light at particular wavelengths. Hydrogen, magnesium, carbon, and other ions leave recognizable features. In a quiet cloud, those features would be narrow. In many quasars, some of them are stretched into broad hills. That broadening has an established physical meaning. Part of the gas is moving toward Earth, so its light is shifted to shorter wavelengths. Part is moving away, so its light is shifted to longer wavelengths. The wider the line, the larger the spread of speeds along the line of sight. In Ton 618, the broad emission lines indicate gas moving at thousands of kilometers per second. That is not ordinary stellar weather. The supported interpretation is gas orbiting or flowing in the deep gravity of a supermassive black hole. Line width gives the first ingredient for a mass estimate: speed. Speed alone is not enough. A small mass can make gas move quickly if the gas is very close. A much larger mass can make gas move quickly over a larger region. The missing ingredient is size. The region that makes broad emission lines is called the broad line region. It is too small and too distant to measure directly in Ton 618. In nearer active galaxies, the size of this region can be measured by reverberation mapping. The central continuum brightens first. The broad lines respond later, after light has had time to travel to the line-emitting gas. A delay of 10 days means a characteristic distance of about 10 light days. Those time lag measurements established a relation. More luminous active nuclei tend to have larger broadline regions. The relation has scatter, but it gives a way to estimate size when a direct lag is unavailable. Ton 618 is too distant and luminous for this step to be a simple ruler. The broadline region size used in the mass estimate is inferred from luminosity and calibrated relations. That makes the result supported, not directly measured. The measurement problem is now narrower. The spectrum supplies a velocity scale. The quasar's luminosity supplies an estimated radius. Gravity connects them. The method is often called a virial black hole mass estimate. The virial idea is simple in outline. If gas is bound by gravity, faster motion at a known distance means a larger central mass. In rough form, mass follows speed squared times radius, divided by the gravitational constant. The real calculation adds a geometry factor. The broadline region is not a neat ring seen from above. It may be a thick disk, a wind, clumps, or some mixture of these. Its tilt matters. Its internal structure matters. Those details cannot be read perfectly from one spectrum. That is why single-epoch quasar masses carry substantial uncertainty. They are useful because they can be applied to very distant quasars. They are uncertain because one observation must stand in for a three-dimensional gas map. For Ton 618, the famous number comes from this chain. Measure the width of a broad emission line, infer the broadline region size from the quasar's luminosity, then calculate the mass needed to bind gas moving that fast at that scale. The chain is real. Each link has error bars. The commonly repeated value is about 66 billion solar masses. In scientific notation, that is about 6.6 times 10 to the 10 masses of the Sun. That value should be heard as an estimate from published scaling methods. It is not a reading from a cosmic scale. It is not a diameter measured in an image. It is not a photograph with a label on the center. The quasar nature of TON 618 is established. The presence of a very massive central black hole is strongly supported by the luminosity and broad-line spectrum. The claim that the black hole is ultramassive, far above 1 billion solar masses, is also supported. The exact value is less secure. Different line calibrations, luminosity estimates, assumptions about broad-line geometry, and corrections for orientation can move a single epic mass by factors of several. A value written with 2 digits can appear more precise than the method really is. The honest statement is narrower and stronger. TON 618 is one of the most extreme known quasar black hole mass candidates, with a supported estimate around 66 billion suns, but the exact mass is uncertain. If a non-spinning black hole had a mass of 66 billion suns, its Schwarzschild radius would be about 195 billion kilometers. That is roughly 1,300 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. Neptune orbits about 30 astronomical units from the Sun. Pluto's average orbit is about 39. The heliopause, where the solar wind gives way to interstellar space, is roughly 120 astronomical units from the Sun. On that calculation, the event horizon radius would extend far beyond the familiar planetary system and beyond the region where Voyager 1 crossed the heliopause. This scale is useful, but it is still a calculation. It comes from inserting the estimated mass into the black hole radius formula. It is not an observed edge around TON 618. For a spinning black hole, the horizon scale and the innermost stable orbit are different from the simplest non-spinning case. The scale comparison remains a way to picture the estimate, not a measurement of a visible surface. The phrase, "the biggest black hole," sounds cleaner than the evidence allows. Astronomical surveys are incomplete. Many massive black holes are hidden by dust, too faint for current selection methods, or too distant to characterize well. Some of the largest candidates sit in bright quasars. Others are inferred from the motions of stars or gas in the centers of giant galaxies. Those methods do not all measure the same things with the same uncertainties. A dynamical mass in a nearby galaxy can be more direct, but it usually applies to a less distant object. A quasar virial mass can reach across the early universe, but it depends on broad-line assumptions. Other ultramassive candidates have mass estimates in the tens of billions of solar masses. Their rankings can change when calibrations change, when new spectra are taken, or when a model treats orientation differently. So, TON 618 should not be presented as definitely the largest black hole in the universe. The supported claim is that it is among the most massive black hole candidates known, and that its extreme estimate makes it a test case for how such masses are inferred. A black hole this large raises a formation problem, but that part is more speculative. Supermassive black holes can grow by accreting gas and by merging with other black holes. The early seeds may have come from the remnants of massive stars, from dense star clusters, or from direct collapse of gas clouds. Which path matters most for the largest quasars is still uncertain. For TON 618 specifically, the light does not preserve a complete growth record. It shows a powerful active nucleus at the time the emitted light left the quasar. It does not show every earlier feeding episode or merger. The extreme mass estimate therefore supports the idea that some black holes reached enormous sizes, but it does not by itself identify the root. Formation histories require population studies, host galaxy measurements, simulations, and better observations across cosmic time. That boundary matters. The mass estimate is an inference with known methods. The growth story is a set of hypotheses being tested against a wider universe. The answer is that TON 618 is weighed by inference. Astronomers do not see the black hole directly. They see quasar light from the gas around it. They spread that light into a spectrum. Broad emission lines reveal very fast gas. The quasar's luminosity gives an estimated size for the broadline region. Gravity then turns speed and size into a black hole mass. That reasoning supports an ultramassive black hole, commonly estimated at about 66 billion suns. It does not support treating the number as exact, or ton 618, as certainly the largest black hole in existence. What remains open is the precise mass, the detailed shape and orientation of the broadline gas, the object's rank among the largest black holes, and the path by which it grew. Better spectra, direct time lag measurements if they become possible, improved calibrations, and broader surveys would tighten those answers. Ton 618 matters because it exposes a larger truth about astronomy. Much of the universe is not known by touching, photographing, or weighing objects directly. It is known by the disciplined reading of light, where a smeared spectral line can become the shadow of an unseen mass. That's why source. If this was worth your time, like it, share it, and tell me in the comments what you want examined next. If you would like to support this work, the Patreon link is in the description.